Level students. So I'm going to be going through this M1 paper from January 2010. So let me know if there's anything you don't get or any way you think I've gone wrong, and I'll try and get back to you either in comments or in person. Right, so let's get started. So for question 1, a ring is moving up and down a vertical pole. The displacement S of the ring above a mark on the pole is modelled by the displacement time graph shown in figure 1. The three sections of the graph are straight lines. So the first thing they're asking us to do is calculate the velocity of the ring in the interval 0 to 2 and the interval 2 to 5. So really they're just testing your understanding of how a velocity relates to a distance time graph. So hopefully you know that the velocity is the gradient. So basically we just need to find the gradient of this first section of the line and then the gradient of the next section of the line. So we can just do that by using bog standard change in y over change in x. So if we look at the first section, our change in y is 4, and that's over a period of 2 seconds. So the velocity will be 2 meters per second. For the second part, so from 2 to 3.5, we probably should write v here instead of m. So our change in y is minus 7.5 because we're going from positive to negative, and our change in x is 1.5. So I make that 5. So minus 5 meters per second, and I'm going to go off the side of the screen. Okay, good. Right, so sketch a velocity time graph for the motion of the ring during the 4 seconds. Right, so we've got the displacement, so we've got to think how a velocity time graph will relate to the displacement. So essentially, we just need to plot the velocity for those different times. 2 of them we worked out, and we've got to have a think about the last part. So here's velocity, here's time. Sorry, this is all over the place. So if we think about from 0 to 2, our velocity we worked out was 2 meters per second. And that's going to be a horizontal line because that velocity is not changing. Then at 2 seconds, our velocity changes to minus 5. So from 2 to 3.5, which is going to be about there. Your graph will look a bit neater than mine in the exam, but it's not really that important how accurate it is. What's more important is the points where it's changing. So between 2 and 3.5, we're at minus 5, and then you've got a spot between 3.5 and 4. We are at 0. So we can do a dotted line going back up to 0 and then make clear that's at 0 from 3.5 to 4. Right, part 3, state the direction of the motion of the ring when t equals 1. So that's it. So if we look at we can look at either graph really. So at t equals 1 here, we can see the ring is moving up the pole. So we've got to check, remember it's moving up and down a vertical pole. And we can also see that the velocity is positive here, so we can say up. At 2.75 we're in this part here, so we can see the velocity is going down, so it's negative, so that'll be down. And then at 3.25 it's still negative, so we can say down again. Right, so let's have a look at the mark scheme. So all they want is, so they don't want a lot of working for this, v equals 2 for part 1, and v equals minus 5. The next one, we can see our graph, so they give you marks for only horizontal lines used in the first 2 parts. What am I talking about? Only horizontal lines and first 2 parts present, so that's your first 2 bits here. And then your final mark for getting the rest correct, so including this. Alright, lovely. Question 2, I'll just get rid of all the incorrect working I just did in my first attempt. Right, so firstly, so we've got a particle of mass 5 kilograms that's moving with constant acceleration. So initially the particle is at minus 2 meters. So that's where the particle is, and it's travelling with velocity 2 minus 3. And then after 4 seconds, it's now got a velocity of 12.9. So the first thing I want us to do is calculate the acceleration of the particle. So these kind of vectory questions are really just SUVAT, but you're doing the x and the y parts at the same time. So here we've got v, we've got u, and we're trying to find a, and we've also got t. So if we sub those in, we've got 12, 9 equals u, which was 2 minus 3, and that equals a times 4. So if we take this vector away from this one, we're going to have 10, 9 minus 3 is 12, equals 4a. So therefore, if we divide the vector by 4, we get a is 2.53. Right, good. So that's part 1. So we got a was 2.53. Next, calculate the position of the particle at the end of the 4 seconds. So once again, this is still SUVAT, so we can think about what do we know and what we're trying to find out. Right, now you've got to spot that actually the particle does have an initial velocity, so it's not starting at 0. So we're trying to find the kind of final position. We know u, again, was 2 minus 3. We know v was 12, 9. We found a in part 1, which was 2.53. And we want to know what happens after 4 seconds. So I would recommend, what would I recommend? My gut says to go with s equals ut plus half at squared. But because we know basically everything else, you can use any of those. So all of these are vectors apart from time. And I've got to remember the thing I just told you not to forget, which was that we do also have a initial displacement. So really, I should be writing this as S0 plus ut plus a half at squared. Alright, so S we're trying to find out. S0 was minus 1, 2. ut is going to be 2 minus 3 times by 4. And then we're going to have a half times a, which was 2.53, times by 4 squared, which is 16. So now we've just got to kind of simplify all this and bring it together. So minus 1, 2, plus, this is going to become 8 minus 12. A half times 16 is 8, so we've got to times both of these by 8. So we'll have 20, 24. And then we can just add up all the x's and y's separately. So minus 1 plus 8 is 7, 7 plus 20 is 27, 2 plus minus 12 is minus 10, minus 10 plus 24 is 14. So that should be our final answer. I'm just going to double check the mark scheme. Good, we're right. Okay, second time lucky. Right, so finally, calculate the force acting on the particle. So here, if you think what's going on, we've got a particle of mass 5, and we know it's got some acceleration in the direction 12, 9. So we just have to use Newton's second law. So remember, force, which is a vector as well, equals ma. So the force is what we're trying to find, and m is 5 because it's 5 kilograms, and the acceleration, again, we found in part 1 was, if I remember right, 2.53. So if we times that by 5, we get 5 times 2.5 is 12.5, and 5 times 3 is 15. So this newtons. So essentially 12.5 to the right and 15 up. Good. So they've got 2 ways. No, they haven't. They've got 1 way of doing it. Okay, sorry, don't listen to me. Right, lovely. So there we go. Moving on to question 3. We've got more vectors here in terms of like i's and j's and stuff. So they've told us I is horizontal unit vector and j is a unit vector pointing upwards, which is pretty standard. So part 1, they've told us force F is minus I plus 5j. So we can think of that as pulling 1 to the right and 5 up. So if we try and kind of picture that, we can see it's moving, it's pulling 1 newton to the left and 5 newtons up. And so this will be F. So the first thing they're asking is to calculate the magnitude of F. So essentially, what's the kind of overall force of F, thinking about these 2 components. So because we can see it's a right-angled triangle, we can just use Pythagoras. So the magnitude of F, so we use these modulus signs to show that, will be the square root of 5 squared plus 1 squared which is the square root of 26 newtons. So you can leave it like that or put it to 3 significant figures if you want. We also want to find the angle it makes between F and the upward vertical. So in other words, the angle between F and this red line here. And because of alternate angles, we know that'll equal that there. So we try and get it into our triangle. So we can see tan alpha, just using bog standard SOHCAHTOA, will be opposite over adjacent, so 1 over 5. So if we put into our calculators, alpha equals tan to the minus 1 of a fifth. That should give you 11.3 degrees to 3 significant figures. Right, good. So for part 2, there's a force G, which is 2ai plus ag, and a force H, which is minus 2i plus 3bj, where a and b are constants, so we don't know those yet. And the force H is the resultant of 4F and G. So in other words, H equals, let me go back to blue, 4F plus G. Right, okay. And they want us to find G and H, so presumably we've got to find A and B. So let's try and use that equation they've given us, sub in what we know about H, F and G, and see if that's going to help us find A and B. So H they've told us is minus 2i plus 3bj, and that's going to equal 4f, so f is minus I plus 5j, plus g, and g they've told us is 2ai plus aj, and I'm being a bit pedantic, so I want to underline all the vectors. So basically the number of i's on the left hand side has to equal the number of i's on the right hand side, and same for the j's. So let's try and expand it all out and get all the i's together and all the j's together. So we've got minus 4i plus 20j plus 2ai plus aj. So if we factorise out I, we'll have minus 4 plus 2a, lots of I, and the factorise out the j's, we've got 20 plus a, lots of j's. And that's got to equal minus 2i plus 3bj. Right, so if we kind of use simultaneous equations, we know this has to equal this, and this has to equal this. So if we pick that first one, that looks pretty solvable. So minus 2 equals minus 4 plus 2a. So 2a will equal 2, so a equals 1. Then look using that 3b equals 20 plus a. We already know a is 1, so we can say 3b equals 21, so b equals 7. Right, so we've got a and b, we've just got to make sure we do go back and actually answer the question. So they wanted us to write down G and H. So G was 2a plus aj, so that's just going to be 2, what am I talking about? 2ai plus aj. Because a is 1 then, that's just going to be 2i plus j, so 1j. Right, good. H is minus 2i plus 3bj. And we know now that b is 7, so this is going to be minus 2i plus 21j. Right, so let's just double check that. So on that next part, you get a mark for setting up h equals 4f plus g, a mark for formulating at least one scalar equation from the vector equation. So what that means is you pick up one of those two simultaneous equations we found, and then you get a mark for finding a and b, and finally a mark for subbing in to G and H. And if you look, even in the mark scheme, they've used column vectors, which look a lot nicer than all those I's and J's. So you can use those interchangeably. And if you actually go back through the working, it makes everything a lot simpler having things on 2 lines. You've got all the I's separate from the J's. Okay, lovely. So moving on to question 4. So we've got a box of mass 2.5 kilograms on a smooth horizontal table as shown in figure 4. a light string AB is attached to the table at A and the box at B, an angle at 50 degrees. We've got another string which is attached to the box at C. This string is inclined at 15 degrees above the horizontal and the tension in it is 20 newtons. The box is in equilibrium. Okay, so we know all the forces on this box are acting out, which is nice. Sorry, balancing out, which is nice. Part 1. Calculate the horizontal component of the force exerted on the box by the string at C. So basically they're just asking us to split this into a horizontal component. So that's going to be 20 cos or sine 15. And the way I remember is this is next to the angle, it's adjacent to the angle, so that one's going to be cos. Okay, now I can't help myself. I know they haven't asked us for it, but I also want to say that's 20 sine 15. So if we've already resolved one, we might as well resolve the other while we're here. So cos 15 times by 20. So it's three significant figures. That's 19.3 newtons. But on our diagram, we'll leave it as an exact answer. And now it wants us to calculate the tension in the string AB. Now they're kind of giving us a hint here by just getting us to find the horizontal component. So if we think about all the forces on this box, so we've got the tension pulling down. And remember the tension is the same here as well. So we better call that T1. Actually, no, we're not, because they've told us that's 20, so it's not like we need two tensions. So we're trying to find this T. So we also know the other forces acting. We've got 2.5 G acting down, the weight of the box, and some reaction force that's stopping it going through the table. And there's no friction because it's a smooth table. Right, so if we look at the only things that affect things horizontally are the two tensions, so the reaction and the weight don't affect it. So if we split this tension, then we can see this one is going to be the cos because it's next to the angle. So that's T cos 50. And this one's going to be sine, so that's T sine 50. So now we can see, because we resolved everything, we can see horizontally that T sine 50 will equal 20 cos 15. So to solve, we just need to do 20 cos 15 divided by sine 50. And I'm just going to cheat because I've left my calculator at school. And that will give us 25.2 newtons. Right. Good. So next it wants us to calculate the normal reaction of the table on the box. So this is similar to what we've just done, but there's more forces acting vertically. Now luckily we've kind of resolved them as we've gone, so we can actually see all the kind of vertical forces acting. So give ourselves a bit more space. Right. So if you think about what all the forces acting vertically, so now we've resolved everything, there's nothing acting kind of diagonally, we can just worry about up, down, left and right. So if you think all the forces acting up have got to equal all the forces acting down, so let's think all the forces acting up, we've got R, we've got 20 sine 15, and that's it. So that's got to equal all the forces acting down, so we've got this 2.5 G, and we've got this T cos 50. So we know we've worked out T as 25.2. Hopefully you've got it in your calculator as something more accurate. So we know that's kind of approximately 25.2 cos 50, so the one acting down. So all we need to do, because we know all these things, we just need to shove into our calculators 2.5 G plus 25.2 cos 50 minus 20 sine 15, and that should give us an answer. And let's just check that. So we should get 35.5 once you've put that all in your calculator. Okay. Right, lovely. So finally, we are told the string at C is replaced by one inclined at 15 degrees below the horizontal. So they're kind of changing it. Instead of going up, it is now going down with the same tension of 20 newtons. So explain why this has no effect on the tension in string AB. Right, so what we need to think about here is basically, can we see the horizontal component is going to be the same, so that's still going to be 20 cos 15, so it's not going to affect the one on this side. And also, the thing kind of balancing out this tension is this reaction force. So we're already getting a force of 35.5 newtons balancing that out. So how do we explain that in an exam? So essentially, all you need to say is that they don't really care about the vertical part. The horizontal resolve part is not changed. So this 20 cos 15 stays the same. So it's accept no reference to vertical component, do accept no change to both components. Blah blah blah. Okay, so you don't need to worry about the vertical. 5, we're given the velocity v of a particle moving along a straight line is given by v equals blah blah blah, so a function of t is in seconds, so they want us to find an expression for the acceleration of the particle at time t. So they're kind of testing, to find the acceleration you have to differentiate the velocity. In just the same way, if you've got a velocity time graph, the gradient gives you the velocity. So if you differentiate, we get 6t minus 12. Right, good. So next, find the displacement of the particle from its position when t equals 1 to its position when t equals 3. So similarly now, you need to know that, well, if I want displacement from a velocity time graph or a velocity expression, I need the area. So we want the area between 1 and 3 of 3t squared minus 12t plus 14. So that means we'll get 3t cubed over 3 is t cubed, minus 12t squared over 2 is minus 6t squared, and 14 gives us 14t. And we need to sub in 3, sub in 1, and take 1 away from the other. So we're doing 3 cubed minus 6 times 3 plus 14 times 3 minus 1 cubed minus 6 times, well, that should be squared, so should that. 6 times 1 squared plus 14 times 1, which gives you 15 minus 9, so in total it's moved forward 6 meters. Right, you are given that v is always positive. Explain how this tells you that the distance travelled by the particle between t equals 1 and t equals 3 has the same value as the displacement between these times. Right, so basically if v is always positive, that means that v is basically the displacement is always moving positive, so the particle is always moving forwards. So basically we've worked out between 1 and 3 the particle has now moved 6 meters forwards. Now if we didn't know the velocity was always positive, it might have moved back 1 meter and then gone forward 7 meters. But because we know it has just been travelling one way, then we know it's just gone forward 6 meters and hasn't been moving backwards or forwards. So in other words, the distance travelled won't be higher. So for example, if it had gone left by 1 and then forward 7, it would have travelled 8 meters in total. So let's see how they sum that up in the mark scheme. So you need to say v is greater than 0, so the particle always travels in the same direction, gets you 1 mark. And another mark, as the particle never changes direction, the final distance from the starting point is the displacement. So you don't need a huge amount of words, but yeah. Right, so now we're on to question 6, so we're in section B. So, figure 6.1 shows a toy barge A of mass 1.5 kilograms on a rough plane. So we know there's going to be some friction acting. The plane is at an angle alpha to the horizontal, and they've told us sine alpha is 2/7. Show that the component of the weight of the barge down the slope is 4.2 newtons. So remember, whenever you're doing these kind of slope questions, 99% of the time it's going to make your life much easier if everything's resolved parallel and perpendicular to the slope. So if you think about the weight of the barge, that's going to be 1.5 g acting downwards. So we want to show that this component is 4.2. So if you think about what that component equals, we've got to resolve it. So this angle here will be the same as alpha, and we can see this one's going to be cos because it's next to the angle. So this one's going to be 1.5 g sine alpha, and we know sine alpha is 2/7. So if you put that into your calculator, you should get 4.2 for those 2 marks. And while I'm here, I'm just going to write that that is 1.5 g cos alpha. Right, the barge is held in equilibrium by a force of 6.4 newtons acting up and parallel to the plane. So we can assume it's going to go down the plane if it didn't have that. Determine the frictional force on the barge and state whether it acts up or down the plane. Well, if it's held in equilibrium, we know there's 4.2 pulling down the slope by the weight and 6.4 acting up. So the friction must be acting down the slope to balance this out. So if we think about left and right, let's call the frictional force F. So we know this 1.5 g sine alpha, which is about 4.2, plus the frictional force has got to equal 6.4. So F will be 6.4 minus 4.2, which is 2.2 newtons. And then you just need to specify that's acting down the plane. Right, the 6.4 newtons is removed and the barge now slides down the plane with acceleration 1.2 meters per second squared. Calculate the new frictional force on the barge. So when you see these kind of forces and accelerations, you should be kind of thinking of Newton's second law. So let's get rid of most of this. So, okay, so we're still interested in that. So think about all the forces that are acting. This 6.4 newtons is gone now, and we know there's this 4.2 newtons acting down the slope. We know there's some frictional force pulling it back. So let's rename, well, let's call this F again, but remember this is now going to be acting up the slope because the plane is sliding down the slope. So let's think about what we know. We know the resultant force going down the slope is 1.5 g sine alpha, which was 4.2 that we worked out in part 1. So the overall force on the barge is 4.2 minus F, and then we know by Newton's second law this has to equal ma. So remember, it's the resultant force on the object equals mass times acceleration. So don't confuse this with the F in F equals ma. The F in F equals ma is always the resultant force. So ma we can actually work out. So we know the mass is 1.5 and the acceleration is 1.2. So I'm sorry this is all over the place. To work out F we have to do 4.2 minus 1.5 times 1.2, and I'm going to cheat because I haven't got my calculator, and so we can see the same working here. That should give you 2.4 newtons, and that's going up the plane. Okay. Right. Determine how far the barge travels while its speed increases from 0.8 to 2. So for the last part, it's kind of given us a bit of respite, and this all just looks like suvat to me. So we know the acceleration. So we know the acceleration was 1.2. We know its speed's increasing from 0.8 to 2. And we want to know S. So you should know all your suvat off by heart, and then know that V squared equals U squared plus 2AS. And then we've just got to sub everything in. So we've got 2 squared equals 0.8 squared plus 2 times 1.2 s. And if we solve that, I'm going to cheat again, we can see the same work in there. We get 1.4 meters. Okay, good. Right, but we're still not finished. Figure 6.2 shows barge A on the same slope with a second barge B of mass 2 kilograms attached to it by means of a light rigid coupling parallel to the plane. The frictional forces on barge B is 0.7 and the frictional force on barge A is now 2.3. At one stage of the motion, the two barges are being pulled up the plane by a force 10 newtons parallel to the plane. Draw a diagram showing the forces acting on each barge. Okay, so if we think about barge A, once again we've got the weight 1.5 g. We've always got a reaction force which is perpendicular to the plane. The friction is going to be acting down the slope because we're told the barges are being pulled up the plane. So on A, the frictional force was 2.3 newtons. And then we've also got the tension in this rope. Now remember with tension, the tension's always the same no matter where you are. So the tension pulling down on barge A is going to be the same as the tension pulling up on barge B, which we can worry about in a minute. So going down from barge A, we've got the 2.3 and T, and then we've also still got this 10 newtons, which is just some force that they haven't specified. So on B, pretty similar, we've got 2G going downwards. We've got another reaction force. We should probably call this R1 and R2 because they won't be the same. We have frictional force once again acting down the slope, and for barge B it's 0.7. So they're trying to help you out here by making you draw a diagram. Right. So now this is really like a connected bodies question. So what I would do is just consider the stuff that's happening parallel to the slope, because we know all the motion is parallel to the slope, and up and down it has to balance out, otherwise the barges would be floating in the air or going through the slope. So they want us to calculate the acceleration of the barges and clearly indicate its direction. Now to simplify this, I want to kind of draw the barges horizontally and forget about all the vertical forces, the perpendicular forces. So we've got this, we're assuming is a tension, and if it's a thrust it'll be negative. We've got this 10 acting this way. If you remember, we've got the 1.5 g sine alpha, which they told us in the first part was 4.2, going this way. We've got 2.3 as well. So this is the component of the weight, this is the friction, this is the tension. We've got this tension acting this way. We've also got 2g sine alpha. So that is the weight component acting down the slope of this 2g, and we've got the 0.7. Okay, so there's quite a lot going on. And this was 2 kilograms, this was 1.5 kilograms. And what else do we need to know? Let's work out this 2g sine alpha. So that would be 4/7 of g. That's because we know sine alpha is 2/7 again. Okay, now what we can do here is we know if we work out the total resultant force on all of this stuff, that has to equal mass times acceleration. And the acceleration is what we're looking for. So the total mass of the system is 2 plus 1.5, so 3.5 kilograms times the acceleration. And we know that has to equal this resultant force. So let's think of all the forces that are acting. We'll assume it's moving to the right. Oh, sorry, we're told it's moving to the right. So all the forces acting to the right, we've got the 10, we've got the T, and nothing else. And then acting to the left, we've got minus 2.3, minus 4.2, minus T, so that's all these three forces here. So we can see the T's cancel out, which makes sense. Minus 4/7 of g minus 0.7 has to equal 3.5a. So we just need to work all that out and then divide by 3.5. So 10 minus 2.3 minus 4.2. You know what, I'm just going to cheat because the calculator on my phone is awful. Right, where are we? Right, so this is our working we've done here. So this is all the stuff up the plane. So the 10 minus, that's both the components of the weight, and they've cancelled out the t's. So you should, when you solve it and divide by 3.5, you should get minus 0.8. So because we get a minus, that means the acceleration is going down the plane. Now, it doesn't mean the barges are moving backwards, it just means they're slowing down because the acceleration is backwards. Right, we also, so now we know that is minus 0.8. We can now start to think about the tension. So there we go, A is minus 0.8, and then you need to say something about saying that's 0.8 up the slope. Okay. So, last part, find the force in the coupling stating whether it is a tension or a thrust. So essentially we need to find one of those T's, and then if it's positive it's tension, if it's negative it's a thrust. So if we just concentrate on this one, we know the overall forces on this have to give an acceleration that way of 0.8. So just be careful with like what's forward and what's backwards. So let's think the overall force going to the left is T plus 4.2 plus 2.3 minus 10, and that's got to equal 0.8 times 1.5. So you might have this all backwards. So you might have it as 10 minus 4.2 minus 2.3 minus T equals minus 0.8 times 1.5, but they're going to be equivalent. So that gives us 6.5 minus 10 is minus 3.5. And this will be 1.2, I want to say. So T will equal 1.7, 4.7 newtons, and that's positive, so we need to say that it's a tension. Okay. So, yeah, there we go. So they've done for barge B, we did barge A, so that's makes no difference really. Newton's second law, and then the answer should be 4.7. Right, good. Okay, so finally we arrive at question 7. It's been a real journey. So, looking like a projectile's one to me. So figure 7 shows the graph of y equals 1 over 100 blah blah blah, so some quadratic. For 0 to 20, this graph shows the trajectory of a small stone projected from the point Q, where y meters is the height of the stone above horizontal ground and x meters is the horizontal displacement of the stone from O. Write down the height of Q above the ground. So really this is just where x equals 0. So we see if x equals 0, these two terms are going to get cancelled out. So it's just 1 over 100 times 100, which is 1 metre. Right, find the horizontal distance from O of the highest point of the trajectory and show that this point is 1.5625 metres above the ground. So we're essentially trying to find the coordinate of the highest point there. Okay, so you've got a couple of options. I would recommend using, because it's a quadratic graph, using the symmetry of it. So we can see this goes from minus 5 to 20, so the midpoint of minus 5 and 20 is 7.5. So we know that find the horizontal distance from O, so we know this distance then is 7.5, and show that this point is 1.5625. So to show the y coordinate, we've just got to sub in the x coordinate. So I'll leave that as a task for you. Sub in 7.5 and then you should get 1.5625 metres. Okay, lovely. Right, part 3. Show that the time taken for the stone to fall from its highest point to the ground is 0.565 seconds. Correct, 3 significant figures. So remember, we're only talking about the y direction here. So I would think of this as a kind of Suvat equation again, where the stone is falling from a height of 1.5625 with acceleration of g, so 9.8. So we can just treat this like a standard kind of Suvat thing. Right, so if we think we want it to travel 1.5625 metres, we know it's travelling with an acceleration of 9.8. So if we take downwards as positive, it makes life a bit easier. So we think once travel downwards at 1.5625, you could do this with an initial displacement and then make A minus 9.8. We know U is 0 because it's at its highest point. V we don't know or care about, and T is what we're trying to find out. So we can use S equals UT plus a half AT squared. So we'll get 1.5625 equals 0 plus 4.9 t squared. So t squared will equal 1.5625 over 4.9. And then if you square root that, I pray for you that you get 0.565 metres. So let's just double check that with the mark scheme. And they're in agreement. They've done a similar thing. So you can use S equals UT, etc. So we want to show that the horizontal component of the velocity of the stone is 22.1, correct 3 significant figures, and deduce the time of flight from Q to R. Right, so remember for a projectile, the horizontal velocity is always the same. So if we know a kind of time and distance, we can just use speed equals distance over time to work that out. So we worked out in part 3 that it takes 0.565 seconds to travel these 12.5 metres. So if we use speed equals distance 12.5 over time, which was 0.565, that will give you 22.1 metres per second. And then if we want to deduce, so the time of flight from Q to R, they're kind of helping us there because we know it's travelling 22.1 metres a second, and to go from Q to R horizontally, it's got to travel 20 metres. So again, there's no acceleration horizontally, so we can use speed equals distance over time. Don't get this S confused with displacement because it's speed. So we've got 22.1 equals, what did I just say? I said a distance, which was 20 over t. So t will be 20 over 22.1, which is 0.905 seconds, let's say. And let's double check that with the mark scheme, because I'm having a bit of a mare this evening. And it's slightly off, and that'll be because I've been using rounded figures because of my lack of calculator. So you can see it can make a difference to like your marks. Okay, good. Right, are we ready for the last part? Part 5, calculate the speed at which the stone hits the ground. So, I think we're going to have to go all the way back to this part 3 to work out the vertical speed it's hitting the ground. So, remember the total speed is going to be made up of a horizontal component, which you know is 22.1, as well as this vertical component. So if we go all the way back to this and think about it falling from that 1.5625 metres in 0.565 seconds and work out its final speed. So we know that it started off at 0, it ended at something that we want to find out. Its A is 9.8, so we'll take downwards as positive. T was 0.565, so we've got enough information to work out the speed at which it will hit the ground. So we can use V equals U, which was 0, plus 9.8 times 0.565, which I think my phone calculator can manage that. 9.8 times 0.565 is 5.537. So we know it's travelling metres per second. We know it's travelling downwards at 5.537 metres per second. So now, to work out the actual speed, we're going to have to use Pythagoras, just like we did on that kind of where we worked out the magnitude of that force F. So it's going right 22.1, down 5.537. So we're going to have to do the square root of 22.1 squared plus 5.537 squared, and that will give you, so through the magic of editing I can tell you that will give you 22.8 metres a second, to 3 significant figures. Good. So just to go through the mark scheme there. So you need to use Pythagoras at some point. We already knew the 22.1, and they've shown another way of deriving that the vertical speed at which it hits the ground, which is the difficult bit. And there's their 5.539. Okay, and mine was slightly off. So, cautionary tale, remember your calculator because it makes your life absolute hell if you don't have one. And that's the end of the M1 paper. So thanks for watching. And once again, if you've got any kind of comments or requests or anything like that, just let me know in comments or in person and I'll try to get back to you. Cheers.